All right, welcome everyone. Welcome to 4.4Con. This is a talk about the cryptanalysis of the Enigma. So my name is Bob Weiss. I'm a PW Crack, president and founder of Password Crackers. I'm also a DEF CON goon because I only wear DEF CON goon t-shirts this week for some reason. This is Benjamin Gatti. We're both from the United States. He's a developer for OpenVPN. Both from the United States. Ben is from Charlotte, North Carolina. I'm from Gaithersburg, Maryland. We wanted to sort of call out, this talk is a little bit timely. This year, I presume everyone knows, but maybe not. This is the 100th anniversary of the birth of Alan Turing. It should be sort of a local cultural hero for you guys. If he were alive today, he would not necessarily be attacking the Enigma the same way that he did in the 1940s. He would not have had, he would have had access to a lot better computers and a lot better technology. He probably would have used it, so we're going to do it the way he might have done it if he were doing it today. The genesis of the talk came out of in a talk I gave many years ago, talking about sort of, we did a Crypto 101 talk. We sort of walked people through how cryptography started off historically. And for each crypto system, we'd talk about how it worked. We'd calculate the mathematical complexity of the thing. And then we'd show how cryptanalysts would break that system. And that worked right up until the Enigma, where we would show how it worked, talk about the mathematical complexity of the system, and there was no crack that we could run on our laptops to break Enigma messages. And it was like, well, you know, hey, it was broken in 1940. How hard can this be? Turns out pretty freaking hard. But that's where this came out of, and I hooked up with Ben, and we decided to take that on and see what we could do with it. Yeah, so demo time. We're going to go right to the demo, and it does take about typically about 45 minutes to get these things going. So Chris Sumner in the back, our speaker coordinator for the week, supplied some text. We wanted to try to do a real demo. So while we have tested various messages while we were doing the development and last couple of weeks, we wanted to get something that we hadn't tested, right? So brand new crypttext. So I know what this crypttext says, right? Because we created it. Theoretically, Ben doesn't, right? So I've given this text to him, and on his laptop, we're now running Enigma crack to try to break this. And is that the top message is what it's going to be, right? Is the best projection?
Yeah. This is the crypttext given.
Okay, that's
and the best solve is in this range.
Right. So currently, what you're looking at in the bottom box is the software's best projection of of the best solution it's found so far. So pretty much gibberish at this point. And say it's going to take about 45 minutes to run through this, so we have to get it started right at the beginning of the talk. And we'll flip back and forth. Ben, if you can kind of keep an eye on it and let me know when and if it starts to pop, we'll flip back and forth. But again, we're doing brand new crypttext, so it's we don't know that it's going to work. Now, typically what happens is the timing of how long it takes us to decrypt is a function of the length. We've gone a little bit long to improve our odds of getting it done during this talk, so we should be okay. It almost always breaks over the long run, right? We just don't know whether or not it's going to break by the time we're done with the talk. So that's the stress point. And as I say, you'll be in it with us and see whether or not we fail completely in this demo or not.
Right.
And we'll take it from there. So again, so why do we care about the Enigma? You know, why are we talking about it? It's 2012. Why do we care? The thing was broken, obviously, in the 40s. It's actually broken a little bit earlier. But there's two interesting things sort of that are going on with the Enigma. The first is it's this inflection point in cryptography. And prior to this, cryptanalysts typically always won, right? It was easier to break codes than it was to create codes. And if you map the complexity of codes prior to the Enigma, it's sort of this line, and they're getting a little bit more complex. And the Enigma is just this massive spike that goes off the chart. It's really where you start to get into modern cryptography. And of course, you know, we all know the story because there's this fascinating World War II narrative about how the Poles break it, and you know, we win the war because of the intelligence that we get from the Enigma messages. So it is this sort of the story that we're all familiar with and that we're all comfortable with, and it's this, again, great narrative. So again, we just wanted to sort of take it to the next level and break it on a laptop in 45 minutes, which hasn't really been done before. So a couple of, you're going to kind of run through the Enigma fairly quickly. First of all, there is no the Enigma. There are multiple versions of a machine that gets created. There's Army versions, Navy versions, 3- and 4-wheel versions, variable reflector versions, etc. So there's no one machine. They're in fact serially numbered, and you can count, you can look at the ones that have survived and identify the machine by the serial numbers, but each of them is a different, not each one of them, but there are many, many different models. So what we're breaking is a typical 3-wheel Enigma. It's the most common version. They do get a little bit more complicated. They get up to a 4-wheel version as well. So we're not doing that, but the software and the methodology could be used to break that. It would just take longer. So these are a picture of the wheels. If you have, the machine originally was supplied with only 3 wheels. So you'd have wheel 1, wheel 2, wheel 3, and you could put them in one of 3 slots. So you could create, what's that, 8 possible combinations. Later, the Germans introduced 2 more wheels. So the machine came with 5 wheels, and choosing among the 5, you could put any of the 5 wheels into any of the 3 slots, and there's a possible 60 combinations of that. So 60 ways. Yes?
Yeah, can we just switch to my screen real quick?
Absolutely.
I want to take you through this screen that he had first, but this is really one of my favorite pictures. This is a more original Enigma machine. You can see the logo here. This is like the first brochure that was ever produced that said Enigma and advertised the product. And just some huge differences to note. There's a printing machine in the back. There's a hand crank here. There's maybe 1, 2, 3, 4, 5, 6, 7, or 8 wheels there, etc. So the machine has morphed considerably. Okay, go back to your screen. By the time we get here, those 8 wheels essentially have been created not by having 8 wheels, but by having 3 wheels and using them twice. This was a kind of a pivotal moment and a huge facepalm, right? We'll get into why it's a facepalm, but so what happens with the electronics is that the signal is introduced by a wheel here you can't see, right? But each of these has a connection here. And then in this wheel, it's rewired from, let's say, here, wraps around and goes under here. And then in this wheel, it may come back up here, and then in this wheel, it may go to a random place. This is the B reflector, which just wires each letter to some other letter. Notice, though, that it doesn't ever wire any letter to itself. It can't do that because it's an electronic circuit, it has to fold. And so the signal migrates back through the path again and comes out essentially in the same electrical circuit that it went in, but at a different pin, and then it goes and lights up a light. In folding this over and reducing from the 8 original wheels to the 3 essentially with a reflector, which is still kind of 4 times that everything, or 8 times that everything gets convoluted, they gave up one critical factor, and that is entropy. Any letter can be encoded to any other letter. It can never, however, be encoded to itself. Bletchley Park wore that like an old rug. I mean, they just took that all the way. The Enigma bomb is essentially based on this defect and other aspects of the discovery, but they lost true encryption really when they did that. They buried it, as we'll see in later slides, with another piece of complexity called the Stecker board, which doesn't exist on the first machine. But in trying to produce something that's more portable, and small and compact, they created the first error. So this was a good illustration to explain what's happening there.
So let me roll through here. So that's a closer up view of the contacts on each of these wheels. But can you put the laser pointer on that notch? right by the
That's
E?
the
Yeah.
notch.
So there's a notch there. And basically, every time a letter is encrypted, the wheels rotate, or the rightmost wheel rotates. So it rotates a little bit like an odometer. And every time we hit the notch, the rightmost wheel pushes the wheel next to it. Right, so it has the effect of rolling over. It's an odometer with 26 characters on it. When it hits the 26th, it pushes the other one. Of course, you could start at 15. When you hit the 26th, it's going to roll over, right? So that notch can be moved as well. So for every one of the wheels that I put in the machine, I can set that notch position. It rotates independently from the rest of the wheel. So that's one of the settings that I need to set. So when I'm setting up my machine, I'm going to specify the order of 3 wheels from 5. So I might say wheel 2, wheel 4, and wheel 5. And then I'm going to specify A through Z for each of the 3 ring settings. And for instance, I would say, KBS. And that would be my ring settings. And those are set on the actual wheels before they go in the machine. That's a little bit blurry. But message settings, once I get that in, I close the top of the box and I rotate the wheels until one of the 3 letters, one of the alphabet letters is showing. That's my starting position for the message setting as well. So again, I can set that to AAA is showing, but any 3 letters of the alphabet. So obviously there were on the previous slide, there was 600 something combinations of ring settings. I'm sorry. The 3rd ring setting on the left would push the 4th wheel, but there is no 4th wheel, so it doesn't have any effect. So you can set it to anything. It doesn't change the machine. So really only 2 ring settings on the 2 rightmost wheels make any difference. But on the message settings, there are 17,576. That should be 2 to the 63 options. 26 to the 3rd, I'm sorry, 26 to the 3rd options for that. And then the plug board is where you get a great deal of complexity. After this goes through, the circuit goes through the wheels, both on the front end and on the back end. Any letter can be connected to any other letter. So I end up with, it's 26 factorial, right?
No, it's a double factorial.
Double factorial. So I can connect H to J, and the first thing that will happen when I press in H is it'll convert it to a J, send it through the wheels, hit the reflector, come back out, and when it comes out as S, S will be converted to D, and D will show up on the light, right? So the plug board is a massive amount of complexity, right? That's where most of the complexity of the machine is, 150 trillion combinations of ways to connect. I'm sorry, another thing. The Germans only use 10 wires. So the maximum complexity for the machine for the plug board is achieved by using less than the 13 possible wires. There's 26 combinations. You could use 13 wires. Adding the extra 3 wires actually constrains the number of combinations that you can create. So the maximum number of combinations of plug board settings is created with 11 wires, but it's only slightly higher than 10. And if it's only slightly higher, I'd rather supply fewer wires and have fewer settings, so they use 10. So that's why they use 10, right? It gets you the maximum amount of complexity because some of the letters are not wired. So that's a sort of brief overview of sort of where you get this calculation. The expected complexity of the Enigma should be, and that should be 2 to the 77th, right? And that is a very complex system. Ben, can you take a look at the software and see how it's doing, whether it's popped or anything at all yet? Very complex system. DES would be 2 to the 56th, and AES would be 2 to the 128. So this is Enigma machine is a little bit is significantly more complex than DES, not quite as complex as AES. Right?
We can take a look at it.
Take a look?
Yeah, we can take a look at it. So, for reasons that we'll explain a little later, what happens when we're braking is we start to get close, and it's important to know that the machine leaks slowly. Modern techniques, we believe, break or don't break, right? But basically, you have to hit all the combinations. In the Enigma machine, for, again, reasons, it kind of breaks in pieces, and you can start to see little sections of words showing up.
That word there, sites. It's a little bit interesting because I know what the crypt text or the plain text is. Right?
So I saw this word, which is 7 letters in a word probably looking like a word. This is starting to happen.
And that right before that, where you were CIAL.
CIA, yeah.
Very interesting. Chris, does any of this ring any bells? Is it starting to look like your abstract? Oh, I'm sorry. So the abstract that Chris gave us was from his talk on the whether or not we could find a psychopath on Twitter. So that's what this is, right? But yeah. So Ben and I know from experience this is starting to get close, right? That we're starting to see glimmers of things. It probably still looks like a lot of gibberish to you guys, but again, already the machine is starting to find stuff.
So this number here is fairly important to me, 9, 19, 10, and the 143. My guess is that it's definitely going to be 143, and then it's going to be fairly close to 9, 19, 10. It might be 9, 20, 10. It might be something like that. But
So wait, let me hop
close.
back, right?
And I might point out, in Bletchley Park, this is essentially what they were working with. They would get gibberish, and it would start to make a little bit of sense, and then they would work out the details from there. That's pretty typical.
So real quick rundown of sort of the where our software ranks in the overall scheme of things. The Polish in the 30s, they are the cryptanalysts of the world, right? They are the world-class cryptanalysts. And you'd think, it's like, oh, well, Turing broke it at Bletchley Park. That's what the story we all know. Really, Marian Rejewski breaks it in Poland in 1932, does two very fascinating mathematical things. He derives the three wheel orders, the pins settings of the three wheels mathematically without stealing a wheel. So he has no access to that, but he's able to mathematically derive it. He's also the input rotor, which doesn't move, but basically starts the circuit going, was switched between the commercial version, which he had access to, and the military version. He's able to figure out what they switched. So the Polish really are the ones that start this whole thing off, get this plate spinning, and really deserve a lot of credit. And again, they are the world-class mathematicians at the time.
Note to self, you want to switch back?
What? We want to switch back?
Yeah. I think it's game over.
Solved. Pwned. Right.
Okay,
so go ahead. Can we read some of this out? Abstract social media sites are now the most popular. Oh, the Enigma has no spacebar. Now the most popular destination for internet users, providing social scientists. Is that something like what you gave us, Chris? It's either that or a really clever manipulation, right?
Right.
So that's effectively what we're doing, right? So demo over at this point.
Wow.
Right.
No demo fail, damn it.
Right. Thank you. Yeah, and we're done, right? As you can go home now because we don't care about the rest of this stuff, right? So.
Could you explain the top line?
Can you leave that up, Ben,
Nope,
and we'll get
it's
back
gone.
to it? It's gone.
So what I'm going to do, because that was fun, I'm going to raise the bar a little bit, and I'm going to shorten the amount of text I put in, and we'll just do it with less text. It's increasingly difficult to do frequency analysis with less text. That's just the nature of the game. So we kind of overshot there. Let's
So yeah, I'm going to keep going with trying to set the stage, right? So the Poles eventually create their own decryption machine in 1938, and then they go dark. They're set back in December of 1938 when the Germans add the two new wheels, and all of a sudden their thing doesn't work anymore. And 1939, the Poles realize, well, and in part because they're reading the German text, right? Nobody knows. We're going to be invaded, and basically Poland is done. So we need to get this intelligence out of the country. So the Poles tell the French, and the French say, "Sacre bleu, what do we do? Call the British." So they have no idea. So they call the British, and the British bring in Alan Turing and spin up Bletchley Park, and and we're all good. And basically what Turing and Bletchley-Park are doing is crib-based decryption, or what we would call today known plaintext attack, right? So they take a series, typically something on the order of 12 characters that they know is likely to be in the message, and they eliminate a whole series of settings. It's all, billions and billions of possible settings are eliminated because they can't possibly generate this piece of plain text at any point in the message. That still leaves them maybe with 100 settings that they need to test, but 100 settings is sort of doable by cryptanalysts, so they give them the 100 settings and they decrypt the messages from there. And remember that they're intercepting, this is also being sent by Morse code, so they're intercepting Morse code from a known station somewhere in the world. And these stations typically had their patterns, right? The things that they would do. So they're a weather station in Paris. The Germans are transmitting the weather, and they do it every single day. So Turing has an idea. We know what they transmitted for the last 2 months, right? So we have a pretty good idea what they're going to be transmitting today, especially since we also know the weather, right? So the weather report, they're able to sort of build a crib around that, and that's what the British are doing. And the British build their own bomb. That shouldn't be 1930, right? That should be 1940. They get their own bomb up and running, and it's a bomb. It's because the machine makes a clicking sound, as far as we know. So they click, 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 click. It sounded like a time bomb, and it's bombed with an E because it was named by the Polish. And so the British get their version up and running by 1940, and eventually by 1941. I'm not sure about that 1930 date. That seems wrong.
Well,
but
1940.
Say again. Yeah, it can't be 1930, but 1940 is too late, so I'm not sure exactly what that date is.
No, 1940
is the bomb? Okay, so that's a typo.
Also, the first couple of years, it's all paper analysis.
Right. And then 1941, they get help from the Americans mass producing. And that's where the company that will become NCR, National Cash Register in Dayton, is brought in. The precursor to that company starts building these machines, and we end up shipping them to Japan as well. Not to Japan, to the West Coast to break the Japanese codes. I will let you pick it up from here. Tell me when you want me to flip slides.
All right, so we started up first just writing the emulator or the simulator to so that we could automate the decryption process and look at the frequency analysis. Essentially doing these kinds of breaks. I mean, if it was the worst case brute force, you'd just try every combination and try the message and then see if the message was in English. The problem is that's still actually difficult to impossible to do. The complexity of the Stecker board is really high, and going through all the combinations of the wheels, both in their wheel orders, there's 60, changing all their individual settings. There's another 26 cubed of those, and then starting the message in any one of 26 cubes different positions is just a huge amount of parametric entropy. 77 bits, I think we calculated.
Right, so yeah, the Enigma machine is, again, roughly 2 to the 77th. And today, in today's world in cryptography, if you've got 2 to the 64, that's basically okay, right? So we're all going to choose something higher, right? We're going to implement 2 to the 128th, but we can't really break anything that's more complex, that has a real complexity of 2 to the 64. So the Enigma machine, if you're going to brute force it, is 2 to the 77th. That's going to be good. That would work, but unfortunately, there are issues.
So we have to do a couple of things. We have to find some weaknesses we can exploit, right? We have to find shortcuts. Fortunately, there are a number of them. We found some. Others have approached this in different ways. But the issues exist for largely the same reason. And then we have to find ways of speeding it up. So the GPU was a great way to speed up the execution. And basically, we moved a great deal of the problem set into the graphic processing computer, which runs parallel processes, maybe hundreds or thousands of individual kernels at a time, attacking essentially the same data set and producing summations of each of these attempts very rapidly. So that was very instrumental. The other thing that we did in combination with that was we broke the problem apart in fairly interesting ways outside the box. Like you can decrypt the code and then you get the code back. But we actually looked at this without decrypting the code. And that was probably one of the more important things we do. We go to the next slide. By chance. This is what I was getting to. You remember the Steckerbrot, for example, right? Again, with a folded architecture, the signals come in and they're remapped. Then they go through the wheels, which is dynamic, and it's moving every character, so it's a different map each character. And they come back through the Steckerbrot and they're remapped out. But the Steckerbrot gets applied at the front and the back. Now there's an interesting story to this. We had a bet with the NSA. Craig came down to the Cryptological Symposium in Charlotte, and Craig works at the NSA, and he has an Enigma machine, and we were talking about this, and it's like, well, if you get one of these Steckers wrong, like what's going to happen? Well, it's like, well, every 26 letters or so, you're going to hit an N, and instead of getting an N, you're going to get a Q, and vice versa. Instead of getting a Q, you're going to get an N. And we're like, hold on, that's fine, but that's only the effect on the outbound side. It's not the effect on the inbound side. The effect of the Steckerbrot on the inbound side is that everything that encoded to a Q will now be run through the machine at the end channel, and you have no clue as to where that will end up. It could end up anywhere. So the Steckerbrot, when it's wrong, has two impacts. It has one on the front and one on the back. These are different, but they're also linked. So if you solve one, you've obviously solved the other. If you can find places where Q's should be N's and places where N's should be Q's, it will also straighten out all the places where the Q's in the crypttext have been remapped to anything, right? So this was, again, one of the problems in folding this space. But one of the ways that we attacked the massive complexity of the Steckerbrot was to look at that and say, when we do a frequency analysis, we expect to see E's rating really high as they do here, and T's rating in second place and so forth. But if we ignore the letter assignments, we can always sort these numbers so that we're looking at the most popular one first and the last second. So we take this one, which is actually English language distributions, right? And then we take the output, we sort it, we ignore the labels, and we compare the two, sorted, and then suddenly it just doesn't matter. The Steckerbrot on the outbound side is completely irrelevant because we're ignoring the labels, we're sorting the Stecker, we're sorting the output only by frequency, and ignoring completely the position that they're in. So we've eliminated the massive amount of complexity of the Enigma on the outbound side. Haven't done anything on the inbound side, but we've completely eliminated on the outbound side. So in our simulation, we didn't even bother with simulating that part of the machine. So we took the machine apart and simulated it in modules. What you got next?
Stecker isolation. Right.
So on the front end, each of these, each Stecker on the front side produces, I wonder what happened here. I think actually I started to run it again and it actually blew up, which is, I mean, just disappeared off the screen, pretended that it wasn't even running in the first place. Not uncommon, by the way. GPUs are really powerful. Let's just say it that way. It will spin out of control and no problem. Things go really whacked. Fairly unpredictable, but they do some processing. Okay, so all the inbound Steckers, right? In frequency analysis of a fairly randomized crypttext, we're looking at the output to see if it matches the graph that you just saw, right? And if it does, then it's language, and if it doesn't, then it's noise. But we could take every character in the inbound text, like the top line is inbound, right? It's crypttext. Every character that is an E in that inbound text is going through what we call the E-Stecker. If we took only the characters that the E-Stecker produces, we could analyze just those characters. And by random distribution and heuristics generally, those by themselves should have the same frequency distribution as language, because there's no bias, as to whether they're assigned to the front of a letter or the back of a letter or anything. These are just random samplings, dippings in, shall we say, of the plain text output. So if we had, for example, the D as the second character, even if we had the D stecker wrong, and all the characters that are Ds were wrong, if we got the E stecker right, and we only looked at the results of the E characters in position, we can determine independently that the E stecker is producing something. So what we're doing in stecker isolation is, rather than analyzing all of the possibilities of the stecker combinations, which is actually 26 double factorial. Double factorial, by the way, for interest, is not 26 times 25 times 24, but it's the factorial of all of the odd numbers. So it's 25 times 23 times 21 and so on. Minus 10 double, minus 6 double factorial. So there's 20 iterations of the double factorial that accumulate the complexity of this stecker combination on the inside. We reduce all of that, right, to just the simple problem of analyzing each of them 26 times. We try the E stecker when it's attached to A, we try the E stacker attached to B, and so forth. All of the E's is tried against every character. That's complicated, but it's nowhere near as complicated as the factorial complication. It's merely 26 to the third power. So that reduces to 17,000 different attempts, and that is approachable on a graphic processing device. And so that's really where most of this just disappears.
So what you're looking at was 60 times 800 times 17,000 times 150 trillion. Got you to the 2 to the 77. And what we're actually running through in terms of the test that we ran for the demo is still the 60 times the 800 times the 17,000, and it's now times 17,000. It's still a very large number of tests that we need to run to do it, but now it is a manageable number, right? It's not 2 to the 77 anymore.
So to explain that, the steckers are complicated by themselves. The problem is we have to rotate the machine and try all the stecker combinations for each rotation. So it's a recursive problem. Next slide. Diagonal, my favorite word. We discussed whether to use the word diagonal a lot, actually. Some of you may know what diagonal means in the context of Bletchley Park. Nobody? He does. Diagonal.
I read it in the statistics story. I can't quite remember.
Right. So apparently Alan Turing puts together a chart he calls the diagonal board. It is actually an electronic device that's added to the machine. It has some extra logic on it. And I'm not actually fully aware of what it does, but it, quote, allows them to solve the steckers. And that's a...
I think it's based on the symmetry of the algorithm. It's on the phone.
It is definitely solving the steckers. We know that much. I've read that much, and we're going to go visit Bletchley in the park. We'll see a little more about what it does. But diagonal really deals with this notion, right, that there are similarities between 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5, as you go through a matrix, right? The similar lines. And we couldn't escape the word. We're applying it, though, in this case. We've moved from the steckers to the wheels. And the wheels have the characteristic that if you physically take apart the wheel and advance it, which is one of the settings that they did every day, as opposed to every message, you're moving the notch, and as a consequence, you change the place at which it advances. And that has an impact. So it's a parametric value, but it is very similar result to not advancing the rotor and instead advancing the message setting, right? Just roll the whole wheel over. You can certainly get to the same electronic equivalent, like many ways. You can roll the notch back this way. I should say the notch also includes the number component. It's the indicator and the notch that roll together. You can change that, but then obviously if you advance it against the other way, it becomes the same electronic connection for that position. But it's not exactly the same because the notch is moved. And so now instead of rolling over at the 26th position, it rolls over at the 13th position. And that has an effect on the next rotor, et cetera, but it's a diminished effect in that when they're close, the amount of error is not very high. So if you're within...
If we take this and we encrypt it using the settings, the ring settings AAA and the message settings AAA, and then we decrypt it using the correct ring settings and message settings, obviously you get a correct decryption, right? This is a sample sentence showing diagonal conflation, right? But if we take that same crypttext that we encrypted using AAA, and we decrypt it using the settings AAD as the ring setting and AAD as the message setting, we get basically the right thing, except every 26 characters we're going to be off by 3. And the 3 comes from the fact it's the spread between A and D.
So what it means is it's synchronized for a while, and then the notch is out of position, right? So,
Right.
so it doesn't notch over, right?
And then it does.
And then 3 clicks later, it does in fact
and
notch
it's
over.
good.
Right?
And then it doesn't notch over in the right place, so it's wrong.
So this pattern suggests that the fast wheel is off by about 3 points on its notch setting, right? But in another example, there'd be whole sections of text that are garbled and then whole sections that are not garbled. And those could be 26 times 26 in periodicity, right? And that indicates that the middle wheel notch is not quite right. So in either case, it's kind of the same. I mean, if you're close, you get most of it, and you get enough to get a signal through. So we don't really have to check every wheel position. We just have to check often enough that we get one of these sort of neighborly hits. If we get close, then we're probably going to get a signal, as we would, of course, in this case, because there's a lot of clear text.
So let's say we had skipped AAA and we just tested this one, right? AAD, AAD, and we get this sample. Well, the letter frequency analysis of this, the chi, is going to show an inflated chi, right? This definitely has some, non-random letter frequencies in it. So then what we do is we say, oh, this setting seems to have popped. It's got good chi. So let's check everything around that. Let's check all the settings that are anywhere near AAD, AAD. And then we eventually check AAA, and obviously the chi of this sample then outperforms this one, and we eventually find the right message. But on our first pass, we don't need to test AAA, AAB, AAC. If we test every 5th one, we're good.
So in fact, we test every 5th entry in the fast wheel and only every 7th entry in the middle wheel, et cetera. And by the time you've torn that apart, the complexity of your inner problem is really quite reduced. And so those are the two things that we did to reduce the complexity of the Enigma machine, faults that are really unreported prior to this attack. And just adding the graphics processor gives us enough processing speed to crack the Enigma on a personal computer. So there's 77 bits of entropy cracked on a GPU, mostly though by finding faults in the underlying algorithm.
So if we had a key, right, a DES key or an AES key with 2 to the 77, we wouldn't be able to do this, right? Because all you get back from that type of a key is, no, that was the wrong key, no, that was the wrong key, no, that was the wrong key, until you get the right one, and then it's yes, right? It's binary. We're doing things to the Enigma to get it to leak entropy. Effectively, we're playing a hotter, colder game where I guess a particular group of settings, and the machine responds back warmer. You don't get that. I can't think of another code that responds in that way. I asked another cryptanalyst buddy of mine, and I was like, what do you call that when a code leaks entropy like that? He goes, I have no idea what you're talking about. so we don't have a name for it. We're going to call it the hotter, colder game for now because we don't have a name. But the practical bottom line is obviously we are not testing 2 to the 77 tests. Now, by the way, if we leave our encryption thing going, it does eventually run 2 to the 77th, right? But we'll be old men before that happens. What we're doing is we're finding the correct answer by filtering up to the top using the hotter, warmer thing, the most probable answers and pushing those up to the top. That's why we didn't know exactly how long the demo was going to take, and eventually it did take less than 20 minutes, right?
Yeah, it's pretty fast.
So it popped pretty quickly. Again, the software would do 2 to the 77th if we just left it alone, but it doesn't need to.
My computer would melt.
So we'd already gone back to the demo, and we've already finished that. We were expecting at this point to come back to it, but I'm going
You
to...
had a question on the demo. You can switch to it now. So I started over with less text, and it's still working on it. But you had a question maybe about?
Just that line of numbers where it says it's
Oh, right, yeah. What were the numbers mean?
Right here, roughly. Okay, so this is the chi, right? This is the it's called incidence of coincidence in some cases, and it's calculated comparing it to a population of English characters, for example, and the similarity that one group frequency of letters has to another.
But it's got a whole row of info.
All right, this is the wheel order. The fourth wheel is in the slow position, the 1 is in the fast position, and the 2 is, sorry, in the middle, and the 2 is the fast wheel position. This 2338 is actually a code that I use so that I can compare 2 settings which have the similar qualities, because you've got the ring setting and the other setting. If you inverse those out of each other and just reduce the 2 of them together to the electrical equivalence, right? That's that number. And this is the wheel order combined together, right? It's the fourth wheel again in the A position, the first in the I position, the 2 in the A as the message started. Now that may or may not be what they actually used, because this one can be off by anything. The A in the first position is meaningless. These are the Steckers. A-L, C-R, D-E, F-M,
Right, so you would...
and so forth.
The Germans would always have used 10 wires, so you'd have 10 pairs of letters where no letter can appear twice.
And this is the message setting. So this is the way the wheels are set up, and this is the position in which they're started. And again, this one can affect that one, so this may also be wrong. But
And this is and the ones that you're seeing up there right now are the best guess that the software has found so far.
Right.
And I say our second run that Ben started right here, which you're looking at, and theoretically this is running, right? It's changing.
it is running, yeah.
Yep, it just changed. It found a better guess. So while this is going, it'll change, and what it now has is a better chi. It's found some message or some set
4.2
of
instead of
settings,
4.1,
right?
yeah.
That's a little bit better, and it'll keep going. But because when Ben ran it the second time, we chose a shorter text, and shorter text is going to tend to take a little bit longer. So this might not finish during the time that we keep talking. It might not though.
So I'll show you what happens in the first. What we do is a series of passes, right? And you can only do that if you have this quality that one pass actually yields hints to the second pass, and then you refine from there. Kind of a hill climber approach. But this is the bucket, right? This is all the values that we experienced in this first test, which is most of them are kind of in this mediocre center, and then there's a few that are extraordinary, right? Like some kind of a lot in that area. This isn't relative because this is not a known plain text analysis. This is actual crypttext analysis. But if it were a known plain text, this would actually be telling me like what's happening to the right answer. Like, is it falling into these buckets or is it being distributed? So this is the bucket in the second pass and its distribution. So this is sort of how we study it, right? We look at all of the distribution. We expect our right answers to be sort of in the upper end. At the back, we have a microphone for questions. We're more than happy to have questions at any time.
I got a quick question. If I actually select a message which particularly avoids, say, the letter E, so I structure my language to mess up the chi, what happens in terms of decryption? I'm thinking particularly of a poem that I once read that actually was a page long and didn't actually contain the letter E.
Yeah, you could salt messages, right, with just an abundance of characters. There was a very famous message that was produced that had only the letter D in the in the text. And maybe you're referring to it, so it sounds very similar. There's a great story. Alan Turing was taking the messages coming in, and he noticed the message like this, and he looked at it and he said, it has no Ds. And indeed it had no Ds. And it didn't take him very long to figure out that the only explanation for a message that had no Ds in the crypt was that the only letter in the plain text was the letter D. And they had instructions, of course, to produce test messages and broadcast at various times, probably to mask traffic and various things, so you couldn't do traffic analysis. And so the radio operator was lazy, probably smoking a cig, and just mashed down on the letter D and produced a series of characters, which he thought was crypttext. But in fact, it was not random at all because it didn't have the letter D. So maybe the answer is there's a lot that could have been done to secure the Enigma machine that wasn't done. That certainly might have played a role.
But our software relies on doing frequency analysis. So if you gave us a short message about the Polish ambassador, whose name is SZKJEWSKYZ, we probably would have a tough time breaking it. Now, eventually, we would get it, right? Eventually, there probably would be some combination of some message in there would break out significantly above random, right? Unless you really threw together a random collection of letters.
Like Welsh.
And I doubt seriously you could bias it by just adding like one character, because it would do very strange things. It would do nothing when it was wrong, right? It would just be noise most of the time. And I think what would happen if you did that is that would become the tell, right? It would stick out of the group. It would show up at some other end of the matrix for that reason. So I wouldn't rely on that. I think that any cryptologist would tell you bad idea.
Right. I mean, and the other thing is, obviously, if you're doing this on a regular basis, right, you're doing more than one. Once I get it the first time and I realize, you're looking for and I get the letter distribution. So we're comparing doing frequency analysis on letter distributions of English, right? And we got our frequency distributions from Wikipedia, right? If you guys were sending messages to each other and we were breaking those on a regular basis, we would eventually create a letter distribution for your messages, right? It would be different than English. It would be your letter distributions. And we would hone in on that. And if you did that and you figured out a way to do this without ever using an E, we would eventually create a letter distribution for you. Just as a for instance, when the Germans were sending Enigma traffic, they have no space bar on the Enigma machine, right? So they use double X is space. So obviously their Enigma traffic, live, real Enigma traffic, would have lots of sets of double X's in it. All right, we would adjust our letter frequencies to expect not only lots of double X's, but would be, if you think about it, a huge preponderance of X's, right? Its X's would be off the scale, and that would be a tell in and of itself. So we would fairly easily adjust that letter frequency to what the target is doing. Did we get anything to pop yet?
Well, we don't have anything popping yet. It may or may not pop in the next period.
Yeah, as I say, this one, the second time around, it's obviously a lot more problematic because we went shorter. So this is where we expected to come back to the demo, do Q&A. EnigmaCrack.com is live. EnigmaCrack contains source code, copy of the presentation, a zip file of test data, and another file, euler.zip, which was for the workshop we ran earlier. But you feel free to go to that. We're going to keep updating that also over the course of, let's say a year or so. If anything happens, we update the code. We'll keep that website updated. And we're going to try to add on to this. We have a plan to do a little bit more with this. There are some unbroken Enigma messages for some of the more complex machines that we might target. There are some enhancements to our code that we want to do. So, and obviously, it's our hope that the community, somebody else may take this and say, you guys suck at programming, and we're doing it better, right? So it is absolutely open for anyone to steal everything that we've done and figure out how to do it better. And if you do that, we're happy to help you. and go over kind of where we came from. And we're also happy to post any enhancements that anyone else does back onto the website. Questions?
I'm just wondering if you've looked at pairs of letter and frequency analysis of those, because they're also pretty predictable for English.
Yeah, so
Right.
bigrams and trigrams have been used by other people in the past. So we did not do that. We didn't need to do it.
We did, though, implement it and ran it a bit. In the end, it really didn't help based on where we are right now. This is working fine, and in part, Prolog is the past is the key to the future, right? The front stackers are the key to the end stackers, and in order to break the stackers, you can do frequency analysis on the front end, or you can do trigram analysis on the back end. You don't really need to do both. Because the front is the key to the back.
Basically, you could, instead of starting off with a series of frequency characteristics for letters A through Z, you could take 26 to the 2 combinations of frequency analysis of pairs of letters and create a frequency chart for that, and then compare the decrypted thing to that if it was a better match, right? What it creates is a problem of, well, where does the pair start, right? Any group, so if you start with 1 and 2, and then you think, oh, well, then I'm going to do, 3 and 4 and 5 and 6, you're always on the even number. Well, was it 3, 2 and 3 are also a pair.
I think it's actually a more interesting question than that, though. If you remember, one of the weaknesses that we exploit was to isolate the stackers and to sort the chai. And doing so actually disassociates the letters from each other,
Right.
in a way that renders bigram analysis and trigram analysis quite questionable, because if we're only looking at the EE characters, right? If you can imagine the slide we had earlier, if we're taking every E in the crypttext and skipping over to the next E in the crypttext and then skipping over to the next E in the crypttext and analyzing those results in the plain text as a bucket, there's no opportunity for bigram analysis. And if we're looking for the E stacker in isolation, we can't really compare it to the next character in the plain text, because, again, we're siloing the problem. So we really have to rely on heuristics at that level. We can't rely on the bigram trigram analysis early on. Now, at the end, when we're just kind of polishing it up, and by polishing it up, I mean, we've solved every 24 out of 26 characters, and we're just kind of looking for the next notch to go into to kind of get the last bit. There's not really much that happens. There's very little time is spent in the later stages of the software. It's really about heuristically breaking the big problem. And the big problem is the stackers. So bigram analysis is problematic, but there's another group that is doing that. Gilligan wrote a paper in about 1995, and he proposed this form of frequency analysis and the basic ideas that we started with. He didn't get to the stacker isolation and the diagonal conflation for various reasons. Maybe he didn't have the computing power to actually execute the idea. Another group came by and they did a hill climbing that does rely on bigrams and trigrams, and it's been very effective against outstanding real transmissions, right? So they've been, but that's a big distributed software. It's very complicated and doesn't run on, by complicated I mean it's distributed to lots of computers that people are running at home in a pretty cloud effort. This is an attempt to create a discrete piece of software that runs on a laptop that anybody can use to crack the Enigma machine. So it really brings the problem down to the individual scale. Because we know the NSA has really powerful computers, right? But if they're going to crack, they could crack things that really ordinary people can't crack. So the bar here was to be able to say that we could crack the Enigma on the machine. And right now, we probably need to use stacker isolation and diagonal conflation to make that practical. But very excellent question.
Any others?
I've got another one if
All right,
nobody
one
else
other-
has.
One other comment. Ben and I were planning to go to Bletchley Park on Saturday. So anyone who is remotely interested in joining us for a field trip, stop us anytime during the con.
Yeah.
Okay, I had another really quick question, which is when you find a word fragment or a whole word, rather than trying wheel combinations around that, have you tried looking at, from the end of that word moving forwards, trying to unravel the configuration of the machine that would actually continue to produce English rather than gibberish?
So I did imagine that the fourth stage, which is where that's handled, could do something more intelligent than it's not brute force, but we go through the wheel order. We go through all the possibilities in that wheel order and analyze all of the settings that produce the same this same number, right? Anything that produces that number is analyzed at this top stage. And that seems to hit it. But yes, one could analyze it in more detail. As I proposed to Bob, we could take every character, right? We could take the first character and put it in a column, all the second characters, all the third characters to the 26th, and then repeat that, right? So we could modulate this into a pile by 26, and look at the chi of every 26 characters. If we did that, we would probably be able to reveal the notch offset, because what would happen is we'd get beautiful language for the first 24 characters of every 26, and then for 3 characters we'd have noise, right? And then we get beautiful chi for the next 23 characters and noise to finish it out. That analysis would probably just tell us we'll move the notch 3 points and we're done. And likewise, we could do the same at the 26 times 26 periodicity and resolve for the middle wheel, and that's all there is to resolve. So there are better techniques that could be used in the fourth stage, but the fourth stage is really not very difficult. There's not a lot of processing because there's not that much to, it doesn't take very long to go through the entire wheel order at that point. It's just a single wheel order. There's, I forget exactly how many it resolves, but it may be as few as 2,000 attempts or something. It takes a couple seconds on the computer.
Yeah, sometimes it's quicker for the GPU to just try them all than to try and be intelligent about it.
The fourth stage is not being done currently on the GPU. That is true, especially in pixel processors. I'm not quite sure that by the time you're doing general processing in the GPU that it quite has that characteristic, but it may have. So it's hard to know exactly. We looked at that this morning in the workshop. We don't have an answer for it.
Thanks a lot.
Yes, thank you all.